This video is going to cover the torsional force diagram and its creation, and if you haven't already seen the axial force diagram creation video, go give that one a look because these are effectively the exact same, just with a different equation. Yes, they do function exactly the same, so if you get one of them down, you pretty much got them both. Now, I will say that the torsional force diagram one's just a little bit more difficult just because of the way that we look at torsion, and torsion is a twisting of the member's axis. So it's not bending moment, right? It is a moment, as we did discuss with our 3D things. It is a moment, but this direction moment creates bending, right? It creates bending upward. So we're not talking about bending moments, no, not that things. We're talking twisting of the member. So say we have this lovely looking cross section. We're twisting this way. We're twisting the member of it, so where now the thing looks kind of goofy, and then it twists over and creates weird shaped stuff looking things. But anyway, we're talking the twisting, where we would have gone from an actual straight-faced square to now a twisted square on the shape. So maybe, it goes back, maybe it untwists, however it's going to do that magic. So we're talking twisting. So this is about 3D things. So get ready to have a whole bunch of fun drawing 3D shapes. Hope you enjoy that. Probably don't. You probably, like me, don't really enjoy doing that on the surface, but that's perfectly fine. We're just gonna kind of give it our best shot and go from there. So how we're going to do this is going to be the exact same way that we did before. For the axial force diagram, and step one is always to find reaction forces. But again, that's a big asterisk next to that because technically the answer is you don't really need to. Is it a lot easier if you do? For sure. But is it required? That's kind of up to you. Yes, that's kind of up to you. You could totally skip it. Maybe it makes it a little bit easier for you, maybe it doesn't. But we're going to see two different ways how you can do things. One where you use it, one where you don't. So you'll understand what I mean here in a sec. Number two, we're going to make cuts. We're going to make cuts every time there's a change in the load. So in this case, we're talking torsional forces. We're just talking twisting. We're not caring about anything else. There's no axial, no shear, no normal, none of that stuff. We're just talking about the twisting. So anytime there's a change in the twisting, either more in the same direction or some in a different direction, anytime we got a new force, we're going to make a new cut. Step number three, we're going to do your favorite. We're going to draw some free body diagrams. Hope you love those. Again, and it's including everything to the one side of the cut. Left, right, up, down, doesn't really matter. You're going to pick the whole one half of the cut and draw the free body diagram for it. Step number four, we have to assume positive internal torsion. Yes, that's the fun part, positive internal torsion. T is for torsion. And how do you figure out what direction is positive? We do that using the right hand rule. Yes, RHR, right hand rule. This unfortunately assumes that you have a right hand. If you don't have a right hand, then you do it with the left hand and you flip the values. Yes, that's effectively it. So right hand rule, how it works, how we're going to do it, is for torsion, you've got a face. Let's look at a face here. So we have a face of a member. This was a very terrible drawing. My apologies. So we have a face, and we're gonna look at this face of the member here, that one. And which direction would be positive for that face? So in order to use right hand rule, you have to figure out where your thumb's pointing, and your thumb is going to be in the positive normal direction. So again, if you haven't checked out that axial force diagram video, give it a look because this will help you a lot. So we're going to go positive normal again is away from the face. So that's positive normal. We're going away from the face of our cut, and that's the direction of our thumb. So take your right hand, put it to where your thumb is going in the direction of the arrow that we just drew, and which direction do your fingers curl? Which direction do your fingers curl? That would be kind of, it's going to come back behind and it's going to shoot around, kind of curl that way. Yes, it's how it's going to kind of curl that way. So it looks a little bit weird. Again, we have our arrow coming out. It's passing over in the front, swirling around there. There you go. It's kind of difficult to really gauge this. let me just try and erase what's going on here so you can get a better idea. So he's passing behind it, whereas this guy's passing over it on the other side. So that's the direction that we're doing. So hopefully you can kind of visualize that. It really, really helps to always draw this normal force direction to always show you where your thumb was pointing. So at any point in time, you can put your fingers there in case your directional arrow is not doing a really good job. Okay, so we're going to assume positive internal torsion using right hand rule. That's really important there. Step number 5, we're going to solve for the moment. It's really simple, right? Solve for t. That's using sum of the moments. But very specifically, we're doing it with an axis. Which axis are you going to do it, right? When we're talking bending, you get to choose. You're like, ooh, do I want point A or do we want point B? But we're not doing bending. No, we're not doing that. So instead, we're going to go about this longitudinal axis. Okay, so we're bending about this axis again, because we're not bending, we're twisting. We're twisting. So it's the sum of the moments about the longitudinal axis of the member. Yes, that's the direction we're going to do it. So we're going to sum the moments about the longitudinal axis to solve for t, and then obviously step number 6, we're going to repeat that every time there's a new cut. So repeat for every cut. All right, that's all there really is to it. Not much. Calculate your action forces. It's a huge suggestion. Please do it. It does make it nice. We're going to make a cut every single time there's a change in loading. We're going to draw a free body diagram for the cut. We're going to always assume that our cut has the positive internal torsion direction found by right hand rule. We're going to solve for this t value by summing moments about the longitudinal axis, and then we're going to do it again and again and again for every cut. So sounds pretty good. So here we go. Here's an example. So for this example, we have this gloriously drawn picture by yours truly. So we have this beautiful picture of a circular shaft here. We have some, let's call them discs or gears, whatever you want to call them, these glorious things here. So these things are attached to obviously the circular shaft, and yeah, they're being twisted. So they're attached to the circular shaft, and we're twisting those things. I'm not going to draw them again because, as you can tell, that's probably one of the ugliest drawings you've ever seen in your life. So I'm going to just not draw the discs again. I'm just going to draw the moments, which is the bendings that they're doing. Hopefully you can kind of see the directions that they're twisting. Hopefully this makes a little bit of sense here. And again, step number 1 is to figure out the moment that's going on over here at the fixed end A. So I'm going to just put TA over here. That's what we want to find. We want to find him first. Now the actual goal of this whole problem is to obviously fill out our torsion force diagram. Right? So usually they're going to be kind of sideways, because drawing these vertically, I mean, you could, totally could. But either way, it's all the same. Don't forget that when you are doing your torsional force diagram and you're going to label it, T for torsion. Maybe you want to go a little bit more fancier than that and maybe write out the whole word. Definitely label your positive and your negative. And then even more so, label your units. So this time in this video, our units are going to be in kip feet. Kip feet. Yes, K dot FT stands for kip times feet. Some people write out kip entirely, KIP. Not me. I'm a little bit too lazy for that. I should, but I don't. So shoot me. So anyway, here we're going to go. We're going to start by summing the moments. Again, we're going to find the TA, the twisting at the end. So we've got some of the moments. We're going to pick a direction to be positive. So we're going to kind of say arcing, and like that motion is going to be positive. I'm going to set it equal to 0. So that is, I know my drawings are horrendous here, but that is the positive direction that I drew TA in. 6 kip feet are going negatively, so we're going to minus 6 kip feet off of it. We got 27, yes, going in the correct direction, so plus another 27 kip feet. Then we're going to swing back over here. We're going to minus 30 kip feet. So that is our direction. That is our equation. So we're going to solve for t at A, and that's going to give us 9 kip feet. 9 kip feet. Now it is a positive number, this 9 kip feet. So the question is, what does that mean? That does mean that the direction that we assumed, or that we drew it in, right? That positive just means that the direction you drew it in is the correct direction. So this was in fact going in that direction. That's all it means. We're just going to come over here and write in a new 9 kip feet. Oh, that is absolutely atrocious with the units. So we'll squeeze the units up here. 9 kip feet. There we go. Looks a lot better. Cool. So step number 1, we determined our reaction. That's always beautiful. So now we are, oops, deleted a few too many things there. So there we go. So now we're going to make our cuts. So again, every time you have a new twisting action going in here, new torsion, that's where we need to make a cut. So let's see, maybe some green, I guess. We'll pick green. So I've got a reaction force, and then I've got this other force, so that's going to be a change. There will be one there. Then there's obviously 2 different directional spinning discs, so there will be a cut there. Another 2 directional discs, so there'll be a cut there. And there's actually nothing happening after D, right? I mean, there's rod here. There's rod here, but there's no actual twisting motion. There's nothing additional happening to it. So we don't need to make a cut. So we only have 3 cuts. That's kind of nice. So we're going to label these. I'm going to go left to right. So this will be 1, this will be 2, this will be 3. And again, the number of cuts you make literally just depends on how long they wanted to draw this stick and how many things they wanted to put on it. Right? That's really all it comes down to. So what we're going to do now is we're going to do cut by cut. So let me see if I can't squeeze some of this in here. Let's get rid of that line, and let's get rid of those 2. Let's draw this up a little bit further. I'm cheating. I already know what it looks like. So we're gonna, yeah, there we go. So we're gonna move that homie up a little bit over here. We're gonna say that's positive, negative, and then we're gonna squeeze in here and make some more space for myself. Yeah, there we go. Cool. So cut number 1. We're gonna solve for that down here at the bottom of the page. Cut number 1. Let's draw a pretty picture. Which way do you want to go? Do you want to include all of the numbers or just the one end? You're probably thinking, oh my god, draw it small. So again, I'm not going to draw discs. Instead, here's my 5-second how to draw a cylinder. You draw a circle, you draw some lines backwards, and you draw a little half a circle on the end, and there's a very beautiful looking cylinder. Yep, there you go. Okay, so we already know that we have this 9 kip feet torsion on this side. What does it look like at the cut face? At the cut face, what does it look like? Let's pick a new fun color. Pink's great. So again, in order to figure out which direction is positive, we're going to come out of the face for the normal. So out of the face for the normal, that's where the direction of your thumb goes, and then your fingers curl in the positive direction. So they're going to curl that way around. So this is T1. This is torsion at cut 1. Kind of irrelevant. You don't really need to really do that, but in case you want to keep up with your nomenclature, there you go. So that's what it looks like. Again, we're just going to sum the moments. Yep. You got to pick a direction. I'm going to pick that this direction is positive. Set it equal to 0. So what do we got? We've got going on, well, there's 9 kip feet going positive, and then, hey, guess what? Also T. Yeah, T1 if you want to call it that. So plus T1. So what happens next is that you get that T1 is -9 kip feet. Oh boy. So what does the negative mean? Again, the negative means that the direction that you drew this arrow, that way, was incorrect. Yep, that was wrong. That was the wrong direction. Could you see it coming? I would hope so, right? I'd hope you're looking at this picture going, wow. Obviously, one of them has to go the other direction. So yeah, so you kind of knew that was coming. So again, that means that it's going in the opposite direction, and the opposite direction would then be making the thumb point towards the face, which is a compression, so that's negative. So long story short, as long as you are actually following this very big and important assuming the positive internal torsion thing, which was found with right hand rule. So again, long story short that way, if you follow this step number 4, this guy, this homie, is very important. If you do that, then when you get a negative number here, again, that directly corresponds to over here. So we get, boom, -9. It's that simple. Yep, it's that simple. So stick with it. Keep making sure you're paying attention to your positive direction for internal, which again, right hand rule. So draw the normal force first. Point your thumb that way, curl the fingers. You're going to see fingers curling that way around, and that's how we're going to figure out which direction to put our internal torsion. If you do that, and you get a positive number, then you draw it on the positive side. You get a negative number like we did, you draw it on the negative side. Okay, that's what it means. That's what it means. So cool. So we did one of those. So let's yeet him off the screen. Whoop. Take you and wee away you go. And now let's go for cut number 2. So for cut number 2, what do we got going on? Well, this time we have included the 6 kip foot force. Yes. So again, we got to draw a circle, straight lines back, cap it off with a half a circle. It looks absolutely atrocious. Good effort there. Yep, looks like a really bad club. Alrighty, so again, we've got our going around 9 kip foot reaction force. Then we have, I'm not going to draw the stupid disc, okay? We got going around this way, 6 kip feet. And then we've got our cut, and the cut's over here. Alright, so which way does the cut go? Again, it's going to come normal, comes out of the face. Point your thumb in that direction. It's going to curl this direction. So this is T2 because this is cut 2. Hopefully really easy seeing it like this instead of with the gears. Maybe it's a little bit easier to identify what's happening with these. So hopefully that's a better picture. But same thing. Continuing on, we're going to sum the moments. I'm going to pick that way to be positive. Trying to give you the biggest archy motion to kind of see what's going on. And let's solve for that. So we're going to set that equal to 0. What do we have? Well, that means we have 9 kip feet positive. Then we've got next up the -6 kip feet. And then we have positive T2. All that equal to 0 there. Solving for T2, so we're going to get T2 is equal to a -3 kip feet. So what does that mean? That means, well, again, it was going in the wrong direction, which does mean that this one is going to be up here, wee, nice and small, -3. Yes, we're on the negative side of that line. Cool, cool. So far, so good. Cut number 3 comes next. So we're going to pick this dude up and do our best to, we're going to try to yeet him off the screen. Make a little more space down here. So away. Come back into this. Let's do cut 3. Now at this point, you're probably thinking, oh my God, do I really have to draw this whole thing? No, but we're gonna. I'm going to show it to you twice, right? I'm going to show you that you could have obviously gone the other direction. So much easier, but we're going to do hard way first. Why not? So again, we're going to draw a little circle. We're going to straight line it back. Woohoo, these are horrible. And then arc it at the very end with a nice fat looking club. Cool. We've got the rotation over here, our reaction. That's 9 kip feet. Then we've got the 6 kip-foot force coming this way. Then we've got, oh, woohoo, over here we got 27 kip feet. Yep, big number there. And then this is our cut face. So yes, we're right after the 27, somewhere in there, so we're right there. Again, positive normal goes away from the face. That's the direction of our thumb on our right hand. Twisting around, we've got drawn it this way. This is T3. You're thinking that's a lot of numbers. Yeah, only 3, not that bad. So we're going to sum some moments again. I'm going to assume that way positive. Set it equal to 0. So that's going to be a positive 9. So we got 9 kip feet. Then we've got 6 going the other way, so minus 6 kip feet. And we got 27 going positive, so plus 27 kip feet. And technically T3 was also positive, so yay, plus T3. What did you find? You found that T3 is definitely not going that way. No, T3 is actually negative 30 kip feet. Cool, so negative 30, yep, not to scale. But there you go, negative 30 on our little graph here. All on the negative side. Coincidence? Well, that just is because that's how I drew the problem. Kind of irrelevant. Kind of irrelevant there. So, yeah, you know, it happens. It's whatever. There can be a mixture of both. They could all be on one side. They could all be on the other side. But you can also have a mixture of both. It's just dependent on the problem. So there you go. That's really all there is to it. But you know, let's check it. Was there an easier way to do cut number 3? You're probably thinking, yeah, that was a waste of time. But let's figure it out. Let's find out. So, oh, we should have scooched out first. So let's move him out of the way, just a little bit out of the way, so we can compare. So I'm gonna just shunt him down some. Scoochy, scoochy. Then let's go back. Let's do cut 3 another way. Let's do cut 3 another way. Let's do it without the reaction force. Could you have done these in the exact reverse order and gotten the exact same chart? Yes. Yes, you could have. So the other one looks like this. We've got, again, same circle garbage. There you go. So, ooh, that was ugly. Hold on, let's try that again. There we go. That still looks terrible, but maybe a little less. Bam, okay. So this time, we're not cutting that face. No, we're not cutting that one. This time, we've got, let's say, 30 kip feet going that way. All right, we got that thing at D. All right, we got that wheel at D. We cut that face. If you just kind of imagine the circle continues, there's the face that we cut. So again, normal goes away from that. So normal's coming out. Again, with the right hand, point your thumb in that direction. And this time you'll find that you're twisting. Give me a good picture here. We're going to twist this way around. Yeah, this is, oops, T3. There we go. We're going to twist that way around. All right, so this time, much easier equation. Yeah, we're going to sum the moments. I'm going to pick that way as positive, set it equal to 0. T3 is not going that way, so that's minus T3. 30 is also not going that way, so minus 30 kip feet. And what did you get? Well, you got that T3 was, holy shit, minus 30 kip feet. Wow, is that what you literally got down here? Yep, is that what you got up here? Yep, so this says minus 30, you say minus 30. This other direction says minus 30. Yep, it's the same thing. So yes, no matter how you're going to do these problems, you're going to end up with the exact same answer, which is lovely for axial and torsion force diagrams. So again, just to recap those steps, solve for reaction forces. It'll do you good if you solve for the reaction forces. It always makes the last cut a little bit simpler. Make your cuts between every single time that the force or there's a change in loading. Draw a free body diagram for each one as we did. Always assume positive internal values for your axials and torsions. And solve for your torsion magically and repeat every single time there's a cut. That's all there's to it. Hope that's pretty easy.